right, here's the idea. We're moving on to falling objects. What you did so far, that entire quiz was horizontal. Everything was here. Okay, horizontal acceleration. Now we're going to do this. But the big idea is that nothing is going to change. Okay? You're still going to use the same formulas. It's still going to be the same concepts. You're still using the big three. Except now we're talking about this, and we actually know more information about this than we do about that. Okay? When we talk about falling objects, if something's here on Earth, it's always going to have the same acceleration. Okay? So on top of knowing the big three formulas, you'll always be able to know, right away you could put down one given that you know, acceleration. Okay? So here we go. Here is the lecture for falling objects. I just like to see who starts copying everything down. You guys are pretty quick. All right, good.
Wait, I'm not done.
Oh, sorry. All right, here's the idea. Galileo is really the scientist that's going to break down gravity and try to understand how it works. Okay, not what causes gravity, but how it works. People knew that things fell. Okay, we had that covered. All right, people understood that things sped up. All right, if I drop this here, it's not going to hurt my hand. If I drop this from a roof, it's going to hurt my hand. Okay, so other scientists could figure out that things would speed up. Hurt, good, okay. Would speed up. So they understood there was an increase in velocity, but they didn't know how. So what Galileo had to do was he had to break down and figure out how things sped up. All right, what the acceleration was going to be. So what he did was, instead of just watching things constantly fall vertically, he used ramps. All right, what he could do is he could figure out how long something traveled after a certain amount of time. Now, it's not like he had a stopwatch, right? He couldn't break out his iPhone and figure out exactly at 1.01 seconds where something fell. But he could figure out set intervals of time. Okay, we know what a metronome is?
Yes.
Tick-tock. Okay. So he could know after 1 second, 1,000 or whatever it's going to be. 1,000. He could figure out where it was going to be. Okay. 1,000, 2,000. Figure out where it's going to be. All right. 1,000, 2,000, 3,000. Figure out what that's going to be. Okay. And he marked it out. And now other scientists were trying to figure out how these distances would relate. Okay, but what he looked at it was, after 1 second, where did it go? Okay, after 2 seconds, where's it going to be? After 3 seconds. Okay, and so on and so forth. Now, he was doing a ramp, and obviously the distances could change. So it wasn't like he was figuring out exactly where every second something's going to be, because he was changing the height. All right, what if it's here? It's going to go a certain distance after 1 second. It's obviously going to be different here. He wanted to know first just the relationship. Okay? However far it traveled after 1 second, let's just say that's 1. Whatever it is. It could have been 1 meter, which really wasn't going to be 1 meter. It could have been 1 marker length. Whatever it's going to be, whatever this length is here, he wanted to know what the relation would be from 1 to 2 seconds, how far. Okay? And what he figured out was, from 1 to 2 seconds, this distance here would be 3 times the length of that. Okay? From 2 to 3 seconds, he figured out that this length here was 5 times the length of that. Okay? For 4 seconds. Can anyone guess what that number would be? 7. 1, 3, 5, 7. Other scientists were breaking it down, but some people thought it would be 1, and then twice as long, and then 3 times. He was the one to figure out these odd numbers. Yes, Robert?
Wouldn't that change if the thing that he was rolling, like, if it was changed? Like, if it was denser, if it was lighter?
No. And we know about mass already, but no, and again, and I'm just talking about a relationship, okay? I'm not talking about a set distance, all right? If I do this, 1 might be this long, okay? Or that long after 1 second. If I go down to here, it's going to be shorter, okay? But he's just talking about compared to what it is after one tick or tock or after 1 second, how long was it after the second second?
So that's should be universally the same.
Yeah. Okay. So, the first basic concept Galileo came up with was that the distance between time intervals, the distance between 0 and 1 second, 1 and 2 seconds, 2 and 3 seconds, would follow a sequence of odd integers. Or just basic English, distance between each second would follow odd numbers. Whatever this distance is here is 1. From 1 to 2 seconds, it's going to be 3 times as much. 2 to 3 seconds will be 5 times as much, and so on and so forth. Okay? Okay. Then you want to look at total distance. Okay? Well, so again, after 1 second, you have a distance of 1. Alright, then what about from 0 seconds to 2 seconds? What's my total distance going to be? 4. What about from 0 to 3 seconds? 4 plus 5 is 9. Very good, very good. Okay? Without doing addition, can you figure out what that next number would be? At 1 second it was 1. At 2 seconds you got 4. At 3 seconds you got 9 times. 16. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. So what he figured out, again, we don't know what this actual distance was, but we knew that, and we keep changing with whatever the ramp was, okay? But we knew that whatever this distance here was, after 1 second, after 2 seconds, it would be 4 times that length, or the time squared. After 3 seconds, time squared, it would be 9 times that length. Okay, so we figured out, if we had to word this and make it sound great, okay, we would say the distance between time integer or time intervals followed a sequence of odd numbers, 1, 3, 5, 7. Okay? And the total distance traveled would match a square of the time. I'm going to have it on a sheet. You don't have to have that written down. But do we see that? That's the big thing that Galileo was able to come up with. All right. Moving on. I'll give you a second to copy that down, right? And I'll talk about it. This would not be really yellow sheet material, but this is a summary of kind of what. That things would speed up. Other scientists knew that too, but he understood that there was some kind of constant times the time that would tell you how fast it was going after every second. That's just acceleration, right? We already know that. Acceleration is an increase in velocity per second. Okay? And he had to figure out what number that was for acceleration. Alright? The distance in between time intervals would match the sequence of odd numbers. 1, 3, 5, 7. Whatever 1 was, between 1 and 2 seconds would be 3 times as much, and so on and so forth. Okay? The total distance matches the square of the time. Whatever the distance was after 1 second. Whatever this distance here is, after 2 seconds, it would be 4 times as much, because 2 squared is 4. After 3 seconds, it would be 9 times as much as that. Okay? Now, do we already have a formula that says something about velocity being some kind of constant times time? The first of the big three, right? Vf equals Vi plus At. That's what that really is. Okay? Do we have a formula that has something with time squared at the end? The big ugly, right? So again, we're going to still use the same formulas we've been using already. It's just that we know what these constants have to be. They're based on the acceleration of gravity. Okay? Can I move on here? So here's the ideas you need to know for gravity. 1, gravity is an acceleration. It's not a force. We'll talk about the force due to gravity. But gravity causes things to accelerate. causes them to increase their speed or increase the velocity every second. All right, and that number is going to be negative 9.8. We're going to say acceleration is negative 9.8 meters per second squared. So every second, when I drop this ball, after every second, the velocity will increase by 9.8. And what does a negative mean anyways? Down, right? Negative just means direction in this class. Okay, so when you see it, we're going to say negative 9.8. We're always going to say, if I throw something up in the air, up is always going to be positive, down will always be negative. Okay? But after every second, something will have increased its velocity by 9.8 on Earth. Always, always, always. That will never change. Okay? In fact, we're going to do a lab down the road. We'll have a lab where we'll go outside, we'll have a tennis ball, and you're going to throw the tennis ball as hard as you can up, straight up. Okay? And with only a stopwatch, if you have a stopwatch and you just time how long it takes to go up and come back down, that alone, you'll have so much information because you know about gravity that you can figure out exactly how fast you threw the ball and exactly how far up it reached before it started coming back down. Okay, with only a stopwatch, with only time. That's because we know so much about gravity. Okay? Alright. Now, you already know, right? When third grade you learned about gravity, or you heard the story about Galileo standing on the Leaning Tower of Pisa and dropped two objects and one was heavier. Yeah? Yeah? Okay. Well, so you know that mass cannot affect how fast something falls. Two objects with different masses have to fall at the same rate. But then you see stuff, everything around you. Okay, well, what if we drop a feather and a hammer? Which one's going to hit the ground first? The hammer. And people will say the hammer hits the ground first because it's heavier.
Less air resistance.
That's the real reason, but most people will say because it's heavier. The hammer's heavier, so it's going to hit the ground first. And what you need to understand is it's not mass. Mass has nothing to do with it. It's air resistance. Okay, Galileo was the first one to mention the feather and the hammer. Okay, and Galileo, when they made the first lunar landing, they dropped a feather and a hammer. Okay, they said, let's see if Galileo was right. And so they dropped the feather and the hammer because there was no air. They both hit the ground at the same exact time. Yes, sir?
How did he figure that out without creating a vacuum? Or did he create a vacuum?
I don't think he created a vacuum. I don't think he had the material or anything to create a vacuum at the time. Some of the stuff that he had to come up with was in his head. You know, what would happen if we got air out of here? Okay? So, you can look it up. Well, I have some stuff out there, but you can look up and see what made him think about the vacuum part. But that's what happened. They finally got to go on the moon, and when they did, you know, we can do this here. We had experiments, but they always break. They even have one. They have one at the Air and Space Museum where you have a little tube, and it's got a feather and a penny, and you let them drop, okay? And when the air's in it, you see the penny hit the ground or hit the bottom right away, and the feather slowly goes down. And then you suck all the air out and do the same thing, but it always breaks, and you always have the feather somehow get stuck in there, and then the feather never falls at all. So, anyways, here's an easier way to doing it. These two sheets have the same mass, right? So they have to fall at the same exact rate. They still have the same mass. So obviously it doesn't have to do with mass. It's not how heavy something is. It has to do with air resistance. Okay? In physics class, we're not going to deal with things with air resistance. Okay? Everything we talk about will be a ball, okay, an arrow, whatever it's going to be flying through the air, something that's going to be dense and not really have much air resistance. Okay, when you go to engineering, when you become an aeronautical engineer or whatever, then you can deal with air resistance. Okay, but here with first level physics, anything we have flying through the air is not going to happen. Sound good? Are we okay with that? And we're not lying to ourselves. A baseball flying through the air. Throwing a football with a spiral, things like that will have much, much less air resistance. Okay, it wouldn't affect it. Alrighty? Okay. Next class, I'll give you a worksheet and start practicing with numbers and all that for gravity. I just want to get those notes out. If you have not done so already, please, please, please do that survey. I'm going to close it out when the bell rings so I can get those surveys in. Okay?